Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on December 8, 2025, just yesterday. It introduces a simple twist on rotary position embeddings that brings back the discarded imaginary part of the attention computation, creating a dual attention signal that preserves more positional information and clearly boosts long context performance. The paper is titled Beyond Real, Imaginary Extension of Rotary Position Embeddings for Long Context Large Language Models. And as we will see later, the implications for scaling models to much longer context without extra memory are quite significant. Also, the authors shared a GitHub repo for RoPE++. Inside, you will find the core Python implementation, configs, and deep speed training scripts for both short and long context runs, plus OpenCompass evaluation configs, perplexity testing on Wikitext and Lambda, and scripts for baseline comparisons and their noise experiments on long context attention. Figure 1 explains that RoPE++ splits attention into two complementary parts that respond differently to distance between tokens. The upper region shows real attention, which focuses more on nearby tokens, so it captures strong local semantics. The lower region introduces imaginary attention, which weights distant tokens more heavily and therefore tracks long-range dependencies. The right-hand plots illustrate that real scores decay quickly with distance, while imaginary scores stay larger and more oscillatory across long contexts. Figure 3 compares how the learned position embeddings behave for RoPE and RoPE++ as the model moves beyond its training window. The overall figure shows that RoPE++ keeps both cosine and sine waves active and varying well into the gray extrapolation zone, while vanilla RoPE trends toward flatter curves there. The two left panels display RoPE and RoPE++ for one ordering of query and key channels, and the two right panels repeat this for the swapped ordering. Together, these panels suggest that RoPE++ exposes more diverse phase patterns at long relative positions, which supports better length extrapolation. Table 2 shows that imaginary enhanced RoPE++ consistently handles long sequences better than vanilla RoPE on synthetic long context benchmarks such as Ruler and Babylon, which stress whether a model can recall information far back in the prompt. The overview of scores indicates that RoPE++ EC gives the highest averages across almost all lengths, especially at 64,000 tokens. The RoPE++ EH configuration usually matches or exceeds RoPE, even though it uses only half the effective cache. Together, these results confirm that imaginary attention heads deliver tangible gains exactly where context becomes very long. Table 1 shows that imaginary enhanced RoPE++ keeps or improves short context quality compared with standard RoPE and other position encodings. The upper block reports results for the smaller 376 million model, where RoPE++ EC gives the highest average score and RoPE++ EH stays very competitive while using half the cache. The lower block repeats this for the larger 776 million model, and the same pattern holds. So across both sizes, adding imaginary attention preserves or boosts accuracy on classic benchmarks like Wikitext, Lambda, and HelloSwag without sacrificing short-range performance. Figure 4 shows that the imaginary enhanced RoPE++ EH variant saves compute resources while scaling to longer contexts. The combined row of plots compares memory use and decoding time for standard RoPE and RoPE++ EH across context lengths. The left two panels cover the smaller 376 million model and reveal consistently lower memory and faster time per token for RoPE++ EH. The right two panels repeat this for the 776 million model, where the efficiency gap becomes even larger at 32,000 tokens. Figure 6 shows how perplexity grows with context length, and it confirms that imaginary enhanced RoPE++ generalizes more gracefully beyond its training window. The four panels cover pre-trained and NTK-scaled versions of the 376 million and 776 million models. In each panel, the RoPE curve rises sharply once the context passes the stable range, while both RoPE++ EH and RoPE++ EC increase more slowly. This gentler slope means the imaginary attention variants remain more reliable when prompts stretch far past the usual limit. So the key message is that treating rotary position embeddings as fully complex with dedicated imaginary attention heads gives both better long-range recall and lower memory costs at scale. More broadly, this suggests that richer positional geometry can extend context without massive model changes. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.